Hi guys, in this video we're going to be talking about concavity and the second derivative. So we've got three graphs here. We're just going to look at this first graph of y equals x cubed. Now let's say I wanted to think about what the gradient would be right at the bottom here. So the gradient of the tangent at that point is going to be extremely large, right? It's a very steep gradient. If I go up a little bit, the gradient's becoming a little bit less steep. If I go up a little bit again, the gradient's becoming a little bit less steep. If I go up a little bit again, the gradient is becoming a little less steep. So from this point all the way up to the y-axis, or when x is equal to 0, that entire region, we could say that the gradient is decreasing. It's slowly getting less and less. It started off very, very steep, and then as we nearly approach the stationary point, so this stationary point here when x is equal to 0, the gradient is approaching a point where it's going to be 0. So from negative infinity all the way up until this point here when x is equal to 0, we would say the gradient is decreasing. It's slowly getting less and less. Now, once we cross this point here, which is our stationary point, now what's starting to happen, so if I think about what the gradient is at this point here, the gradient of the tangent is increasing, or has gotten larger. If I think about the gradient of the tangent at this point, it's getting larger. If I think about the gradient of the tangent at this point, it's getting larger, and it's going to continue increasing forever. So we could say that anywhere right of the y-intercept, we could say that the gradient is increasing. Now in maths, we've got words that we use for these two situations. So the first half here, we would say that this region is what we call concave down. So the concavity of the graph is down, meaning that the gradient is becoming less and less and less. Then, using a bit of intuition, we could say that this other case is when we are concave up, because the gradient is continually increasing. Now, we're still looking at this graph here. At this point here where we have a stationary point, that is the exact point where the concavity changes. That point is called a point of inflection. And the way that we can find a point of inflection without having to actually go and graph this function, there's something different about points of inflection in math. So at a point of inflection, something happens. The second derivative at that particular point is going to be equal to 0. So if you ever have a situation where the second derivative of a function is equal to 0, that tells you that that point is a point of inflection. We already know that if we've got a point where the first derivative is equal to 0, then that's what we call a stationary point, which is generally a maximum or a minimum. Okay, so this first situation here, that's only one example of a point of inflection. There are some other examples. A point of inflection does not always have to be a stationary point. In the first situation, it just so happened that our point of inflection was a stationary point, but that's not always the case. If we look at this second example here now, so let's just start right from the bottom here. Notice the gradient is quite steep at that point. If I go up a little bit more on my graph, it's still steep, but it's starting to get less steep. At this point, it's still steep, but it's starting to get less steep. At this point here, the gradient is equal to 0. Now, at this point here, the gradient is a negative value, right? It's sloping downward. So notice at this point here, the gradient is still decreasing. The gradient is still going down. And what's going to continue to happen is it's not actually until around this point here, which is represented by the red dot, it's not until about that point where the gradient, what's going to start to happen is from that point onwards, if I draw the gradient of a tangent at any line, at any point, sorry, the gradient of the tangent is always going to increase now. Notice it's always going up. So this point here is where the concavity changes. That's also a point of inflection. Notice these 2 points look very different. One's a stationary point, the other's not a stationary point, but they are both considered points of inflection. So I've just made this graph up. I don't actually know what this function is, but if I did know what this function is, what I would know is, let's say that we're looking at the x coordinate here. So let's say I'm thinking about that x value when we do get a point of inflection. I definitely know that if I found the second derivative of this function, and if I substituted x into here, the second derivative is going to be equal to 0. If we wanted to, we could draw the same sort of lines as we did before underneath this graph. So all the way up until just after the y-axis, so this point, this entire region we would say is concave down. And then therefore, this entire region, which really goes on forever, I shouldn't be really drawing straight lines because it goes on forever in both directions. That region we'd say is concave up. Now we can also think about concavity when we're thinking about quadratic equations. So if we just look at this green function first, right? If I do the same sort of gradient analysis, at this point here, the gradient is very steep, but it's very negative. So right now that gradient, the slope of the tangent, is going to be quite a big number. It's probably, I'd say that the slope of that tangent at that x value is probably like negative maybe 20. It's going to be quite large. If I choose a different point, I've just randomly made up negative 20. It might not be. If I choose this point though, notice we still have a negative gradient, but that gradient, maybe that's negative 10 now. If I find the gradient at this point, maybe that's negative 5 now. At this point here, right, the stationary point, my gradient's going to be 0. And then my gradient is going to be increasing at this point, it's going to be increasing at this point, and it's going to continue to increase forever. So notice in this situation for the green graph, what's actually happened is the gradient is actually always increasing. So from negative infinity, right, all the way to positive infinity, right, the gradient is always increasing. So this entire graph, or that entire function, is what we call concave up. So using a similar approach, you'll find that this blue graph here, it's going to be concave down because the gradient is always decreasing. So at this point here, the gradient is quite steep and it's always decreasing. It's starting to get less and less. Or I should say it's starting to get more and more negative. Like the gradient is sloping downward and downward with larger values. So this entire graph would be concave down. So there are 3 main takeaways that you should have gotten from this video. The first takeaway is that a point of inflection is where the gradient shifts in concavity. The second takeaway is that a point of inflection, when we find the second derivative is going to be 0 at a point of inflection. Third and final thing, an easy way to remember if something is concave down or concave up, if you get that confused, the way that I remember it is I think about, for concave down, gradient is decreasing. So the gradient is getting smaller and smaller. For concave up, the gradient is increasing. That's it for this video, guys. Thanks for watching.